This will be a simple tutorial on how to find max flow in a network. It's part of a larger topic in computer science, which is flow networks or network flow, and also part of Ford-Fulkerson algorithm. So gradually we are going to ease into a Ford-Fulkerson algorithm, starting from a simple algorithm. And also we are going to be talking about max flow and mean cut. So for those who do computer science who have seen this topic before now, you see that it seems a little confusing. So I'm going to make it really very easy for you to understand starting from here. So just follow along as we go. Also, I would like to remind you to subscribe and also subscribe to my channel by clicking on the subscribe button below this video so you get updates when I make new lessons. And also, if you have some topics you'd like me to treat or some observation, please leave it for me in the comment box below this video and I'll get back to you. Alright, let's get started. So now the max flow in a network is simply a way to make very efficient use of the network capacity. So a network may be a computer network that has bandwidth. How can you use the network links so that you make efficient use of the bandwidth of this link? So the best way to understand it is illustrated using graphics. So let's go ahead and start. So let's take a typical network. This is the initial network, and the numbers we have here is the capacity of the network. So we want to assign flows on the edges of this network so that along the line we have the maximum flow possible on this network. Now, one thing you need to know about flow is that there are two laws that you need to apply when you are talking about flow. So if you have a capacity on this network, you can have a flow capacity of 20 on this network. You can have a flow of 30. The reason is because the flow has to be lower than the capacity. Also look at this node. If you check the incoming flow into this node, you see that the incoming flow here is what? Is 20. Outgoing flow okay, incoming capacity is 20. Okay, fine. So outgoing we have 30, we have 10. So it means that if we have a flow of 20 here, we can have a flow of, let's say, 25 here. We can have a flow of 30 here because now we will violate the conservation constraint. So there are two constraints. Conservation constraint simply says that sum of incoming flows through the network is equal to the sum of the through a node. Sum of the incoming flow through a node is equal to the sum of the outgoing flow through the node. So that's conservation. The capacity constraint is that the flow should always be below or at most the capacity. So the flow cannot exceed the capacity. So that is the capacity constraint. So want to be assigning flows without violating any of this constraint and also get the maximum flow through the network. So let me erase all this. All right. So the first thing you want to observe in a network before you start assigning flows is to observe the maximum capacity of this network. So the maximum capacity of this network is the sum of the flow into the sink or into the terminal node, which is also equal to the sum of the flow going out from the source node. So it's normally written like this. The sum of the flows out of S. Sum of the flow on all the edges going out of S. And you can also write it for the sink. So the first thing we want to do is we can actually start from 0. Let's say we assign a flow of 0 on all the nodes and gradually increase it. That is what Ford-Fulkerson is telling us. But let's actually assume that we started from 0 and we have increased all the way to 20. So let's take the first step. The first step, we started from 0 start with a flow of 0 on all the edges. So the red numbers is the flow, colon, and then the capacity. That is the normal notation or the standard notation of flow and capacity. Sometimes it's written as flow slash capacity, sometimes in some textbooks. The next step is to choose a path. This is called ST path. Choose a path from the source to the terminal or to the sink. So I've chosen this path, SUVT, right? So note that the edges have a direction. The edges have direction pointing forward, and this pointing forward. So ST path is a directed path from the source all the way to the sink. So that is the next thing you want to do. And the next thing you want to do is to increase the flow on the path by 20, right? So at this point, I'm increasing from 0 to 20. I'm increasing from 0 to 20 here, and I'm increasing from 0 to 20 on that path, right? So not on any other path, but just on this path. Now, at this point, let's examine the network to see if we violated any of the constraint. And if you check, you find out the capacity constraint has not been violated because we have 20 coming into you and 20 going out from you, 20 coming into V and 20 going out from V. So the capacity constraint is still in order, and also the conservation constraint is still in order. So at this point, we kind of got stuck because we have a flow of 20, but the capacity of this network is 30, right? So take note that the network have a capacity and the nodes have capacity as well. The edges have capacity as well. As I told you that the capacity of the network is the sum of the flow, the sum of the flows going into the terminal, which is actually 30. So if we have a flow, if we achieve the flow of 20, we actually need to do a little more because the capacity is 30. But now we are kind of stuck because we have 20 here. If we are going to increase, we can't increase anymore in this part SU. We can increase in the parts U and V, right? And we can't increase on the part VT. So we can't actually increase on the part UV without violating any of the constraint, because if we increase on this place, we can't push out. So if we increase here by 10, we can't actually push out anymore on this part. So we can now look at alternative path, and that is SVUT. So we're going to take the next step, which is very important in Ford-Fulkerson. We are going to subtract a flow of 10, let's say minus 10 on this part. So if we subtract a flow of minus 10 on this part, we now have 10. And that means that we have a flow of 10 that we can push through UT, and a flow of 10 that we can also add into V. Because now we have V is having a short of 10 units, because we have 10 going in, 20 going out. So we need 10 to come in to complete it, and we need in UT we need 10 more to as well complete. So that we are going to do in the last step, where we increase the flow on SV, that is this line, by 10, which is the same 10 we subtracted from UV, and also increase the flow on UT by 10. So at this point we have a maximum flow, and now you can see that the flow here is maximum at 30, which is actually the most efficient flow we can get. So this is basically the intuitive way of solving the max flow problem. Now we are going to look at the algorithm to solve this problem, and that is the Ford-Fulkerson algorithm. But before you are going to understand the Ford-Fulkerson algorithm, we need to understand how to create a residual graph given a flow network. I'd like to thank you for viewing. I would like to remind you to leave a comment if there's something you find that you would like me to know.